Morning, everyone. This coming week, 4 days, we have 5 sections to do. So give you an idea of what the first 2 sections are going to be. We did a little intro last time, so at least we'll be able to get into it relatively quickly. Section 11.1 is an intro to what are called sequences. And the other 10 sections in chapter 11 are all about series. And the series is what you get when you add up all the terms in a sequence. So the kind of things we're going to practice today are evaluating terms of a sequence, either by being given a formula or by using what's called a recursive relationship. We're going to talk about a sequence being increasing or decreasing. If a sequence is always increasing or always decreasing, it's called monotonic. And we're going to look at how do you test for convergence or divergence. We've seen that. And a little bit about finding formulas. So that's definitely going to get done today. And it depends on circumstances. But at least we'll get started on intro to series, and we'll talk more about that later. But here's a kind of hit list of things that eventually I'll get through. Okay, now to do you a very quick recap. A sequence is a list of numbers that goes on forever and that has some kind of pattern to it. And one of the most common ways is to describe the sequence by giving a formula. And I'm now going to switch my notation over. Evidently the textbook likes AN instead of UN. Neither of which are good letters of the alphabet when it's a sequence, but it is what it is. If you're given a formula and you're being asked to find, say, the first 3 terms, you just go 1 squared plus 1, 2 squared plus 1, and 3 squared plus 1. So obviously, you'd just get your calculator and you'd do it. I have some notes on 11.1. If you go and look at those notes, there's actually a section that tells you how you can get your TI-84 to do the whole damn thing for you, so you don't have that monotonous job of calculating the same formula 5 times, because I think the going rate is write down the first 5 terms of a sequence from its formula. And that will work provided that it's a formula. Now, some sequences, this one's an example of it. Actually, if I get the next one. It's just by inspection, is it pretty obvious that this sequence, if you looked at what would happen as it tends to infinity, that this sequence would be infinitely large, and we call that situation, we just say that it diverges. On the other hand, you might get a sequence that has this formula. Now, if I calculate its terms, you'd get 1, a quarter, 1/9, 1/16 forever. And I think it's pretty easy to just tell by looking that the limit of this sequence would be in fact 0. And when that happens, we say it converges, or to be more precise, it converges to 0. Because when it converges, you should tell people what the number is or are. That seems pretty familiar, pretty reasonable. If someone gives you a formula, you can find 5 terms, whatever they ask you for, and we'll go into it in more detail. You should be able to tell whether it converges or diverges. And remember, diverges is a catch-all for it doesn't have a limit. So just so that we don't get caught up in the fact that we think all diverges are infinite. Do you know if I did the sequence AN, the formula for it was sine of n. Can you imagine the first term would be the sine of 1, I mean 1 radian. Then it would be the sine of 2 radians. Then it would be the sine of 3 radians. Forever. These do not get bigger and bigger. Do you know the sine of 100 radians could be negative 0.7, and the sine of 101 radians could be positive 0.1. In fact, if you plot and make the x-axis n and the y-axis the value of the sequence, which is quite common, if you plot it and you have like term 1, term 2, term 3, term 4, and so on, you make no attempt to say this is accurate, but what you would get is maybe something that looked like this. Can you imagine it would be random dots to eternity? Can you imagine the sine of 1 billion and then the sine of 1,000,000,001 would just bounce somewhere between 1 and -1 in no particular pattern, actually quite randomly. So that's a different example of diverging, right? It doesn't have a specific limit. It just doesn't have a limit. So going to infinity is called diverging, not having a limit. Now you might say, well, the limit is a sine of infinity, and sine of infinity is infinity. Wrong. Sine of infinity is an unknown number ranging somewhere between -1 and 1, and it depends on what number you think infinity is. That makes sense? You can pick anywhere on the sine curve and stop, and that would be one location, but there are many. Now, notation. I can give you a formula written like this. That's its formula. That's the sequence. I can put it in curly brackets, which is the same thing. I can put it in curly brackets with n equals 1 to n equals infinity on it. How else can I do this guy? No, I think that's probably it. They are all equivalent. They're just so that if you see something that looks like that, where you recognize that it's a sequence and it's just written down in this curly bracket notation. This here is basically a subgroup of this one. They just tell you a little bit more about where to start and where to finish. So far, so good? Now, let's look at evaluating a formula that has recursive. What you do here is that you tell people how to get the next term. En plus 1 is typically the next term in the sequence. And it is given as some combination of 1 or 2 of its previous terms. And then you have to have some seed values. In other words, you have to be told at least a couple of numbers to start the whole process. So for instance, if I wanted to find A2, it would be A1 plus A0. So this would be 1 plus 1. Which would be 2. So I think down here I'll write what these sequences are. Now if I want to get A3, it would be A2 plus A1. A2 is this guy. A1 is this guy. And I now have 3. Can you see what sequence is going to get generated by this recursive relationship?
Fibonacci?
Yeah, the Fibonacci sequence. You could have a recursive relation written something like this. There's a little bit of argument about these initial values. Sometimes some textbooks will say this, and some textbooks will call the first one this. I wish I could take over the world. This guy up here, I would call the top one A1 and the second one A2.
Am I frozen?
I can hear you, Christopher, but
And I think we lost him. Yeah, he has gone. Donald Robertson has left the building. Hooray for dual overhead hamster cage internet. Yay.
Sorry about that. I was just. No, we don't need to leave since the host was dropped. Stay. That's like me just saying, I'll go out the room for 2 seconds, and then everybody says, oh, he's left, we better go home now. Give me a break. Almost get killed on the rush out there. I have no idea what happened there. I was in mid-speech or whatever, and suddenly I get bounced right out, which is really annoying.
When in doubt, blame the gremlins.
Oh, I think I've got some good ones coming through. Right, so we got to this term here, right? So I'm going to use the A1 notation for the SAID. So here goes. If you wanted to find A2, you would go 0.1 times 10 plus 10. That would get you 11, right? And if you want A3, it's 0.1 A2 plus 10. And this time you'd get 1.1, I believe you would get 1.1. You'd get 11.1 and so on and so forth. So if I give you a formula in the usual sense, like something like this, do you feel comfortable about finding the first 4 or 5 terms? If I give you a recursive relationship formula like this, you feel comfortable about the first 5 terms. Now, there are differences between these two ways of describing a sequence. If I give you a formula up here, the stuff that's up here, if I put it over here, if I give you a formula, can't you find the 100th term directly by just plugging 100 into n? If I ask you for the 100th term of a Fibonacci, or the 100th term of this fella here, don't you have to find the first 99 before you can get to the 100th? So computationally, these recursive relationships are not as user-friendly. But that's the way they are created. But if anyone comes up with a formula of this type that does the Fibonacci sequence, I would love to see it. Because as far as I know, no one's found one. Now, maybe wrong, but no one's found a non-recursive formula. I can create one myself the other way. Okay, so I'm checking that off my checklist, right? Evaluate terms of a sequence, either formula or recursive. Let's look at increasing, decreasing, and monotonic. For these, you have to have a formula. So recursive relationships or sequences are not going to be our main theme. Our main theme is going to be what can we do with sequences that have precise formulas. And so we're going to talk about monotonic. This is its definition. A sequence is said to be monotonic if it's always increasing or always decreasing. Seems reasonable. You will find that sometimes you will say that it is monotonically increasing or monotonically decreasing, which is nice. But very often people just say increasing and decreasing. Now, not all sequences are monotonic. Here's one. This -1 to the n is actually quite a common theme. You'll see a fair number of formulas that use it. Essentially what happens is when you plug 1 in, isn't the answer going to be negative? But when you plug 2 in, won't this be positive? When you plug in 3, it's going to be negative. And when you plug in 4, it's going to be positive. So if I find A1, it ends up being -1/2. If I get A2, it ends up being +1/4. If I get A3, it is -1/8, and when I get A4, it is +1/16. Would you agree that that sequence is not increasing or decreasing? In fact, it's doing, I guess, the opposite of that, isn't it? Doing both continuously, going up, but then coming down, going up, but then coming down. If you plotted this guy, he might look something like this. And although you are not meant to join the dots, it might help to visualize it a little bit. Would you agree that this chunk of change here, these sequences, although they are not monotonic, aren't they converging to 0? You can visualize it here. So increasing and decreasing doesn't necessarily mean that just because you're monotonic that you're going to converge to something, or just because you're monotonic means that you're going to diverge, or not being monotonic has any influence on it. I can create equations that jump up and down like this, but get bigger. Suppose that 1/2 to the n was 2 to the n. Wouldn't it go -2, +4, -8, +16, -32? Can you imagine those zigzags getting bigger and bigger zigzags? Isn't this one here much more like a damped oscillation kind of thing, where each bounce is a little bit less than the previous bounce? And so this would converge to 0. So how do we tell if a sequence is monotonic? Well, you have its formula. If you see that guy there, so if you see a -1 to the n, or a -1 to the n plus 1, or a -1 to the n minus 1, sometimes they do one of these 3 versions, some kind of formula. Doesn't matter what it is. If you see this guy, it's not monotonic. And you might say, well, how do I know that? Doesn't these guys generate the plus minus pattern? And would you agree if something's positive, then it's negative, and then it's positive? Would you agree it's not always increasing or always decreasing? Isn't it going up and down? That's one test, if you like, for something being monotonic. But for the majority of situations, you have to do it using Calc 1. Is that sequence generated by this formula increasing all the time or decreasing all the time? So that would make it monotonic. Right? Or is it just random, sometimes up, sometimes down? Can you tell by looking at its formula what is likely to happen? Okay, if you put in 1, you get that. If you put in 2, you get that. If you put in 3, you get that. If you put in 4, you get that. Can you visualize it a little bit better? What's happening as we progress?
It's increasing.
It's increasing. Can you see it now? You might not have been able to see it in the formula, but can you at least see it if you do the first 3 or 4 terms? Now, you're not allowed to say, I did the first 3 or 4 terms, therefore I have proved that it's increasing. Math doesn't work that way. You can't prove by inspection, although a lot of engineers might disagree with that premise, that if you can show that it works 4 times, that's proof enough. Right? I built my last 4 bridges and not one of them fell down, so whatever math I was using is working. Of course, the 5th bridge is the one that does fall down, right? So you need a little bit more advanced. So essentially what you do is you differentiate this. To be precise, En is actually a function of n, right? So you pretend, and this is the purest, that we are pure mathematicians, we look at the real valued function. Now, for sequences, n must be 1, 2, or 3, right? But for a real valued function, can x be 42.1 if it likes, or 3/4? But what this is saying to us, and it's pretty decent math, would you agree that this function, as far as increasing and decreasing is concerned, behaves the same way as the one I'm interested in? Would that seem reasonable? If this decreases, won't that decrease? Seem reasonable? Right, now, from Calc 1, don't you have to differentiate something to find out if it's increasing or decreasing? And I'm going to differentiate this fella, and I'm going to prove that for some value of x greater than or equal to, I'll figure out what it is, that the derivative is positive. Because if the derivative is positive, doesn't that mean it's increasing? If I can prove that the derivative is less than 0, then that's how I prove that it's negative. Now, the reason why we have this little get out of jail free card is, can you imagine that there might be some situations where the first 2 or 3 terms of a sequence kind of randomly jump around a little bit, but after term 3, it increases forever. Or after term 3, it decreases forever. We accept that that's likely to happen, so that when we talk about monotonically increasing or monotonically decreasing, we're allowed to forget the first couple of terms, just to the sequence kind of settles down to what it's really trying to do. So that might be x greater than or equal to 4 or 2 or something. Well, here it goes. Call that f, call that g. F dash g, take out a f g dashed over g squared. That's a 1 times x plus 1. Take away an x times a 1. Oops, sorry. All over x plus 1 squared. You get x plus 1, take away an x, all over x plus 1 squared. In this case, you get that. So the derivative of the sequence function is this fella. And then you can just say this. Would you agree that for x greater than or equal to 1, this is always positive? Would you say that would be a sensible conclusion? Can you plug any number you like, including 1? You could plug in -20 as well, but we're only interested in 1 or beyond, right? Would you agree for this here, 1 plus whatever it is squared, right? That's positive, and 1 over positive means it's greater than 0. So our conclusion is it's monotonically increasing. Now, if you differentiate a function and the derivative is equal to something that you can prove is negative, right, for x bigger than 2, say, then it's monotonically decreasing. If it's neither, right, can you imagine a function that bounces up and down? No. then it's a little bit harder because calculus won't prove that. What it will show you is, won't you have a derivative function that can be positive and negative forever, right? Sometimes it'll be positive, then later on it's going to be negative, then later on it's going to be positive again, and that would be not monotonic. Now here's the second part to that. It's called bounded. A sequence AN is bounded above if there exists a number M, capital M, such that so can you imagine a sequence that never gets bigger than 4? Then we say it's bounded above by 4. That seem reasonable? Can you imagine a sequence that never gets bigger than 4? That would be bounded above. Now, a sequence AN is bounded below if there exists a number little m such that the sequence is always bigger than that number. So can you imagine a sequence that's always bigger than a half, right? Every single term is bigger than a half, right? That would be an example of being bounded below. And a sequence is called bounded if both above things are true. Okay, let's look at this fella here. Now, what do we know about this sequence? Well, haven't we already proved it's increasing? Right, we just proved that a few moments ago. Let's look at bounded. Would you agree that this thing is bounded below by 0? Would you agree that every single member of this sequence, that's these guys up here, would you agree that they're all bigger than 0? I mean, they're all positive, right? So they're all going to be bigger than 0. So this is bounded below 0. Now, a little bit harder. If you look at the first 4 terms of the sequence, they are getting bigger, but they're not getting bigger like they're going to go infinite on you. Would you agree that this fella here is never going to be 1? Won't it always be a little bit less than 1? Now, my argument would go like this. Would you agree n over n would get you 1? But n over a number that's a little bit bigger, just 1 bigger than n, won't this give you a fraction that's a tiny bit less than 1? So this is bounded above by 1. So if you get a question that says, here is a sequence, is it increasing or decreasing? You're going to use calculus to find out. And then you might be asked, is it bounded above or below? In this case, it's bounded below by 0 and bounded above by 1. And then there's a little theorem, a little test, and it says the following. If a sequence is monotonic and bounded, it will always converge. So what it says is, if you've got a sequence that's always increasing, but it never gets bigger than 1, and it's just an arbitrary number, you could say it'll never get bigger than 2 if you like, it's still true, it's going to converge to something. You may not know what it's converging to, because sometimes the formula is just ridiculously ugly. Can you imagine, instead of something simple like that, that I put a whole horrible mess of sines and e to the ends on the top, and n cubes and square root of tan x in the bottom, right? Some ridiculously ugly function, right? I might not be able to know what it converges to, because, you know, not everything is easy to find its limit. But if I can prove that it's increasing or decreasing all the time, monotonic, and that it's bounded, the theory says that it's definitely going to converge. Can you imagine something that's getting bigger and bigger, but there's a ceiling to how big it can be? Doesn't it have to level off somewhere? It might not level off at the ceiling, but it has to level off somewhere. That's essentially what the theory says. You've only got a finite amount of space, so you have to level off. Okay, are we happy about how you would prove a function is decreasing, increasing? You need another one? No? Last chance. You're the ones that have to do the homework. Okay. I'll call that good. I've forgotten my little list during the rush. Well, I know what's coming up anyway, so I guess it doesn't matter. How can I lose something in 6 square feet of real estate? It's a rhetorical question. I am capable of doing it, because I've just proved to myself that I have by losing my list. I won it. It's mine. It's my list. Here we go. There it is. Increasing, decreasing, monotonic, right? According to your lot, you're comfortable with that process. I'm happy. Next chunk of changes, we're going to look at convergence and divergence, and how that we would solve that situation, right? So put my little list out the way. There are a number of techniques for finding does a sequence converge or not. Essentially, what you need to do is you need to solve this problem. What's the limit as n tends to infinity? There are certain things that can happen. It ends up being a number. It ends up being equal to 42. Hitchhiker's Guide to the Galaxy reference, right? It could be. If it is a number, we say that it converges. And if we want to be really precise, it converges to 42, right? Or whatever the number is. Second situation, it goes infinite on you, right? So the limit ends up being infinity. Plus or minus, nobody cares. In that situation, we just say it converges. But we don't typically want to or even care that it converges to infinity. Converges is good enough. But there is a third possibility. And that is that it doesn't go infinite on you, but it doesn't go to a number. Sin n is a good example of that. Won't that just randomly bounce between values somewhere in the region -1 to 1 for eternity, right? So in those situations, there is no fixed limit, right? There's no one number that it hones into. And in that case, we also call it converges. And we don't care that it converges because it had no fixed limit. It's just called, oops. Nobody caught that deliberate mistake. In those two examples, we call them diverges. That's better. Are we good? Right, so let's look at the practicalities. L'Hopital, divide top and bottom by n cubed, plug in infinity to see what happens, and by inspection. It's an interesting term, we'll see what that looks like. Well, let's look at the limit as n tends to infinity of 5n cubed plus 4 over 4n cubed plus 2n. Now I can find the limit of this sequence by L'Hopital. I can also do it by dividing the top and bottom by n cubed method, which I call brute force. Both will tell me the same answer. Technically speaking, just to keep the math lawyers happy, that's really the guy I should be differentiating if I'm using L'Hopital. Don't you have to be a function, a continuous real valued function, to be differentiated, technically? Isn't a sequence of dots with gaps between them? So technically they don't have derivatives. Points in space, 2D space, don't have derivatives, right? So it might be being a bit lawyerist, but technically that's what you do. That's why you're allowed to do it. And the argument goes that this function and that function will behave the same. So if this one has a limit of 4, so will that. If this diverges, so will that, right? Now if we do L'Hopital, the usual thing is equals with an L above, so everybody knows that it's L'Hopital. You do the limit as x tends to infinity, and the top guy gets me 10x squared, and the bottom guy gets me 12x squared plus 2.
That's Robertson.
Technically, yes.
Wouldn't that be 15x squared on top?
Yeah. Did you catch that deliberate mistake, everybody? God, that lie's running short. If my brain is already 3 lines ahead of here, which doesn't help. Technically speaking, shouldn't you put infinity in, but you still got indeterminate form. So you do L'Hopital a second time. I'll try and get this one right. You get 30x, and 24x. The x's cancel, so you get this guy, and eventually it simplifies down to 5/4. And that's essentially L'Hopital. L'Hopital is going to be really useful for functions that are well, you can do it for rational functions that are polynomials. I know you can, but I think L'Hopital's better use is for weird functions, you know, things like sine of n or sine of 1 over n cubed, or things with e to the 1 over n or log n, you know, anything that's got something a little bit messier, right, that you can't just deal with. This fella here, of course, couldn't you just divide the top and bottom by n cubed? In which case it would become the limit as n tends to infinity of 5 plus 4 over n cubed and 4 plus 2 over n squared. And I'm running short of room here, but don't you basically do brute force then? 4 over infinity gets you 0, 5 plus 0 gets you 5, 4 over, well, 2 over infinity is still 0, so 4 plus 0 gets you 4. Do you see you get 5/4? Now, you might just say, to heck with it, L'Hopital works for everything, I'm going to do L'Hopital. And you'll probably be fine, but not always. Suppose you try to do L'Hopital on that guy. Well, you're going to find the limit as x tends to infinity of 3x squared over x to the 4 plus 1. And you are going to end up being in a whole load of hurt. What are you going to get when you differentiate this guy? Well, aren't you going to have to call it x to the 4 plus 1 to the half? Aren't you going to have to differentiate that guy? Would you agree that when you differentiate the guy, it's going to be an ugly thing and there's still going to be a square root? Which means that you've turned one ugly fraction into a different ugly fraction, neither of which you know the limit to. So do you see that L'Hopital isn't the only guy in town? There are some circumstances, there's an example of one, where L'Hopital really isn't going to be your friend, right? Can you trust me? I don't want to spend the next 5 minutes doing the rest of this. You do it your own. That guy there ends up just as ugly as this guy here, right? And you keep doing what you're doing forever and you'll never get out of a hole. So I suggest that the divide top and bottom by n or n cubed or n squared technique would be much better suited to this particular circumstance. Now, I'm not demeaning L'Hopital. L'Hopital is brilliant. I mean, it can be used tons of times. I'm just saying it can't be your only tool in the toolbox, because there are certain functions, and I'm going to show you another one after this, that L'Hopital doesn't work for. Now, you have to divide the top and bottom by something here. Would you agree that the top power is n squared? A lot of people unfortunately see the n to the 4, but they don't see the square root that it's inside. Isn't the square of n to the 4 really just a hidden n squared? So when you have the same power of n on the top and bottom, don't you just divide top and bottom by that power of n? So in this case, n squared. Now that's going to get me 3 on the top. Dividing by n squared is really the same thing as dividing by the square root of n to the 4. So that's why that becomes 1 and why that becomes n to the 4. Are we happy about what I just did there? The n squared had to be converted into a square root so that I can divide like with like. And dividing that by n to the 4 gave me 1. Dividing that by n to the 4 getting that. Now if you do brute force, would you agree the answer's 3? So you got to be aware that there are just some guys out there who don't want to play with L'Hopital, right? They just, some sequences just don't. Now, there are ways that you know what the answer is going to be without doing too much. Would you agree if that top power was n cubed, just for argument's sake? Wouldn't this thing, wouldn't its limit be infinite? And so it would diverge. Because there's an n cubed on the top and there's a thing on the bottom that's only really worth n squared, right? That's by inspection, right? N cubed on the top, n squared on the bottom. Isn't the n cubed going to beat the n squared and make the function, make the sequence go infinite on you? Suppose the bottom was n to the 40. Again, by inspection, shouldn't you be able to look at that and just tell what it's going to do? What would it do in this case then? Cube on the top and a 40th on the bottom. The limit would be?
Wouldn't it be 0?
Yeah, be 0. Now, unfortunately, I don't have any, I wish I had the power to change this. A lot of the questions in the homework just ask you, does something converge and diverge? There's only 2 buttons to press. Well, you not press one and when it's wrong, press the other. Because what's going to happen in the final is I will be looking for it working. And if you press the right button and I don't see working, you get 0 points. And if you press the wrong button, but I see working that is right, but you screwed up in the working or you only done half the working, at least you're getting partial credit. So you got to do it the hard way so that you've got practice. Otherwise, you can just say, I don't know how to do sequences and series, but I'm really good at guessing, especially when there's only 2 choices. Don't do it, right? I'm just warning you, in the long term, it's not a good strategy because you're really learning nothing. You're just saying, I can guess, and I'll guess until I get it right. And we are good. So we have dividing technique. We have L'Hopital technique, right? What other techniques? Well, I have to introduce you to a new guy. He's called factorial. Do you know anything, heard that term, seen it before? Great. For those who have not then, 7 factorial is 1 times 2 times 3 times 4. I'm only going to do this once. Here looks like that. Some of your sequences, thankfully not too many, are going to have factorials in them. And they won't be numbers, they'll be n or n plus 1 factorial. So here are some examples of that happening. Here's one with 2 factorials in it. One's called n plus 1 factorial, it's on the top, and one's called n factorial and it's on the bottom. And we are being asked, does this converge or diverge? That's basically what you're going to be asked a lot of the time. Any gut feeling? Do you think this is going to converge or diverge?
Converge.
Okay. It's a gut feeling. Nothing wrong with gut feelings. Half my gut feelings are right. When they do end up being right, I pat myself in the back and say, I'm a pretty good mathematician. I figured that out before I did all the proof. And then the other half of the time I'm wrong, and then I get kind of, oh, I didn't think that was going to help. Well, let's try and figure out how we would do this. Factorials have to be dealt with in a very special way. You can't use L'Hopital on something. There isn't a derivative of n or x factorial. Right, there just isn't. No, nobody's created it. I'm not even sure if it even exists, and we just haven't found it yet. It might be a function that has no derivative because it's impossible to have one, right? It might be. But L'Hopital's out. Dividing top and bottom's probably not going to work. I could certainly put in 1, 2, 3, 4, 5 and have a look at what the answer looks like. And if I did that, you'd find out it diverges. But instead, I'm going to do it old school. If I wrote down n factorial, wouldn't you go 1, 2, 3, 4, 5, all the way up to n? So that represents n factorial being written out in full, right? 1, 2, 3, finished times n. Now, what would n plus 1 look like? Well, wouldn't you go to n and then you'd have another guy called n plus 1? Do you see that there's a lot of carnage about to happen? They cancel, they cancel, they cancel, they cancel, whoever they are. Won't they cancel? And which means that this guy is actually that guy. Now, can we do a brute force on him? Of course we can. It diverges. So if the top and bottom have factorials, you might want to work on simplifying it. And then once it's simplified, you can figure out, in this particular case, it diverges. So if your gut feeling said it converges, you're going to have a look, as I would have if I'd guessed that. And you'd say, oh, I wasn't expecting that. Now, suppose I switch them around. Suppose I put the n factorial on the top and the n plus 1 factorial in the bottom. Can you see that the end result would have been that guy? And that would have had a limit of 0, and so it would converge. Exactly. Now, sticking on the factorial theme, you cannot do calculus on this. You have to do by inspection. That's just a fancy word for I know how certain things get big, and I know that certain expressions get bigger quicker. In other words, they are intrinsically larger numbers than other things. N factorial is fighting e to the n here. If n factorial wins, the limit's going to be infinity. If e to the n wins, the limit is going to be 0. There isn't a halfway house. Just trust me, there isn't. Well, it could be 42, right? They kind of agree to disagree and they balance out. No, these situations are either diverge or converge to 0. So we need to have a kind of hit list of who's the biggest guy in town, right? And then who's the next biggest guy in town? And then all the way down, who's the guy that nobody really bothers about because he never gets big that quickly. So here is the ultimate list of bigness, made up term. Nothing gets bigger, at least anything we're going to see, than n to the power of n. Just pick a number like 100. 100 to the power of 100. Well, actually 10 would do. Isn't 10 to the power of 10 massively big? He's the biggest guy in town. After n to the n, n factorial. There are some textbooks that put this list in. I don't think this one does. Can you just trust me that 10 factorial is pretty massive, right? And 100 factorial is scarily massive. In fact, if you go to your TI-84, I think your TI-84 keels over and dies around about 75 factorial. In other words, the number's so big it can't do it anymore. Who do you think's next?
X to the n.
Well, we'll put like a number like 2 to the n and 5 to the n. Yeah. Agreed. I'm only putting e to the n in, but e to the n's a placeholder. Won't 2 to the n and 7 to the n and the 10 to the n also belong in this group, right? Something to the n. Now, within that family, you can actually have little battles. You know, if 2 to the n was fighting against 3 to the n, wouldn't 3 to the n beat it? Right? Now, after that, you then get things like powers. So what would one try and do? I'm only putting in n squared as a member of this family, but technically n cubed, n to the 4s, right? And this guy has 2 to the n and 10 to the n, right? They're all family of those guys, right? So polynomials come next. So you might think, why should this beat that, right? Well, if you do 2 to the power of, let's do a comparison. Let's 2 to the power of 100 versus 100 squared. Right, I just switched, right, switch the base and the exponent, right? That's essentially what the difference between these is. Isn't 2 to the power of 100 phenomenally big? And isn't 100 squared only 10,000? Have I convinced you that exponents beat powers? Agreed? Not much left here. Who do you think comes next?
N.
Well, yeah, I guess n is the weakest of that. But I think n belongs to this family. It's just the poor relation, right? It's the poorest one in this family, but it's still in the family, right? N's like the last one in the family, right? So up here it'd be n, right? Go even smaller than n.
Is it the reals?
That's just a, oh, you mean like a number, like 5?
Yes.
Yeah. That's not in my list, but technically speaking, I guess I should put that number in my list. I'm going to hold my thought about that one because I'm not quite sure where to put it yet. I think I do know where it's going to go. But I'm, like 5, right? Just a number. Yeah, that does belong on the list, but not yet.
Fractionals.
Yeah. Would you agree the square root of n eventually gets infinite, but isn't it not very good at doing it? Square root of 1,000,000, right, is 1,000, right? It's big, but anything else using 1,000,000 is much bigger.
Very slow.
Very slow. So this is fast. This is like jet rocket fast. And this down here is like, forget it, slow. Right, last couple. Do you know the next one after that is log n? I know that's to the base n, but you could have base 10 and so on. I'll give you an example. It's easier to do in base 10. Isn't the log to base 10 of 1,000,000 just 6? You get old waiting for that to go infinite. I mean, it does it really slowly. Right, and I guess, although I didn't think about it until someone mentioned it, 7, i.e. a real number, never gets infinite. Would you agree that's like never being infinite is the slowest you could ever be? Now, how does this family of expressions work? Well, once you know the order, you can use it to find whether a particular sequence converges or not. Take that fella. Oh, Travis, what's your question?
So if you had a situation like n to the n to the n.
Oh, God. Yeah, that would be n to the n.
Okay, but would it also be like n to the n to the n factorial? Is there like a hierarchy?
Oh, God, no, let's not go there. Yes, you could say, does an e to the power of n factorial beat an e to the power of n to the n, and so on and so forth. But then your head hurts. So yes, there will be nuances above that, but we're looking at just basic building block shapes. I would hate to figure out what does e to the power of n to e to the power of n factorial. Does that beat n factorial to the power of n? And weird combinations like that. I'm sure there's a rule. I guess if I thought it through, I would look at each one on its merits and then say this one wins, because one of them will win, right? One will be faster at going to infinity than the other, right? In this case here, who's going to win the battle? N factorial or 3 to the n? Who's going to get infinite first?
3 to the n.
Well, 3 to the n is here, and n factorial is here. So who's going to win?
N factorial.
And if you win, and you're on the top, you diverge to infinity, right? You diverge. And if you win, and you're on the bottom, won't you converge to 0? So if you ever get a question like, does this converge or diverge? Do you see that I'm doing it by inspection? I'm just looking at it and I say, this guy in the top is going to win the battle of how fast you can get to infinity. And if the guy in the top wins, your answer will always be diverges. And if the guy that's going to win this little battle, right, it gets to infinity faster, is on the bottom, it's going to be converges to 0. So how about 2 to the n over n squared? Who's going to win?
Two to the n.
So what's the limit of this fella?
Infinity.
Infinity. Now, if you can memorize this or whatever your brain does, sometimes your brain just says it's obvious that that's bigger than that, in which case you've already got that list in your head, even if you don't know how to write it down. Can you imagine that this group of questions is going to be diverges box or converges box, and there won't be any working that I would expect to see in a final. Whereas guys like this that you had to use L'Hopital, I think those are different situations. Are we good on limits of sequences? You want to see some more examples, or do you feel comfortable about how to find the limit of a sequence and converges stroke diverges? I got one thumbs up. Have I got any thumbs down? Last chance. Oh, I got tons of thumbs up. I'm good. I'm happy. Okay. Right, so last guy in town, find the formula. Well, you will be given a numerical sequence, and our job is to find its formula. And some of them, we did some of this last Thursday, have a particular shape to them that we recognize. And if we recognize the shape, we can create the formula. And they even have names for some of them. You remember arithmetic sequence? You start with a number, and then you continually add the same amount. In this case, aren't you adding 2 every time? And when you see that pattern, it's called an arithmetic sequence. Now, how do you get its formula? If you continually add 2, it's 2n. If you continually add 5, right, you start with a number like 2, then you add 5, get 7, add 5, get 12, add 5, get 17, and so on. Whatever the constant of addition is, 2n. But normally that isn't the final part of the answer, because if this is going to work, doesn't it have to match up with the position in the sequence? So for instance, isn't the 4th number meant to be 7? Well, 2 times 4 is 8, and it's not what I wanted. So pick one at random, like the 4th term, and add or subtract whatever it takes, it'll be a number, to make it work. So that is how you do any sequence where you start at some unknown number, doesn't matter what you start with, but you add the same amount every time. The number that you add goes here, then pick one of the positions at random and tweak it. So it'll be 2n plus 1, 2n minus 7, right? I'll have that kind of looked at. Wish I hadn't picked this one. This is called a geometric sequence. Now, what makes a geometric sequence work? Right, you start with some random number, and then what do you do to get all the numbers that come after that in the sequence? For instance, how do I get from 3 to 12? And then how do you get from 12 to that guy? And how do you get from 4 to 8 to that guy?
You multiply by
3 times n plus 1.
Oh, okay, well, we'll do the times 3 part. But not 3 times n plus 1. I don't think that would work. If you have to generate the formula for a geometric sequence, and that has one feature, and it's not 3, it's actually 4. If you take a number and multiply it by the same amount continuously, it's called a geometric sequence. The formula for a geometric sequence is I don't know, maybe that's what the person a few moments ago was talking about. This is AR to the n minus 1. A is the first term. R is called the common ratio. Would you agree in this case the common ratio is 4? Now that in this question becomes 3 brackets 4 to the power of n minus 1. And I find it helpful to put the Rn minus 1 term inside brackets so things don't look like 34 to the power of n minus 1, for instance. Do another geometric one. Suppose I start with 10, then I get 5, then I get 5 halves, and then I get 5 quarters. That is also a geometric sequence. The first value is 10. The common ratio in this case is what fraction?
1/2.
1/2. So my formula for finding any term in this geometric sequence is 10 times 1/2 to the power of n minus 1. Now, side issue. If you have a geometric sequence, well, rewind. If you have an arithmetic sequence, won't the limit be diverges to infinity in every single case?
Yeah.
Right? So if you ever see a sequence like that and then it says, does it converge or diverge? If it's arithmetic, it's pretty obvious. Now, on the geometric sequence world, sometimes they converge and sometimes they diverge, and it'd be nice if we could figure out which. In this case here, would you agree that it's going to get bigger forever, so it diverges to infinity? In this case here, would you agree that it converges and it's going to converge probably to 0, right? So how do you tell? Well, it's all to do with the absolute value of the common ratio, the absolute value of R. When it was 4, it diverges. And when it was 1/2, it converges. Not only does it converges to 0, and that always diverges to infinity typically, or at least diverges. Suppose R was 1.8 and suppose R was 0.8. I can tell, without knowing anything else, that that guy diverges and this guy converges. Where do you think the boundary point between the R value, that's the boundary point between where geometric series sequences converge or diverge? 1?
1.
Right. And here is the places where converge happens. If R is any number between between -1 and 1. Now, on this side, you're allowed to equal 1, which is the weirdest geometric sequence in the world, so I'll show you what it looks like. Pick a random number and multiply it by 1. Pretty close to the most boring sequence in the world. Pretty close. I think the one that might win is 0, 0, 0, but that's about it. Now, on the other side, you see that only numbers that are a little bit bigger than -1. So -0.9 would converge, right? And our value of -0.8 will converge. You might wonder why there's not an equals 1 in that. Let's put an example. If you do 5 and the common ratio is -1, that means you multiply everybody by -1, okay? Well, won't this guy become -5, but then this becomes 5, and then this becomes -5 forever? You see it's a bouncing between two numbers, so it diverges. So if you know it's a geometric sequence, isn't the only thing you need to really pay any attention to is the R value as far as convergence goes. And so we've got a little test here. There we go. Now, arithmetic and geometric are reasonably easy to recognize. They have a shape. You start with a number, you add 5, add 5, add 5. You start with a number, you times 2, you times 2, you times 2. They're pretty easy to see. And then you have that last group, that just kind of falls into, there is no, you know, they're just one-offs, right? So here is a one-off. And that would be considered the first, second, third, and fourth. I kind of like these questions because I like puzzles. Would you agree it's a fraction, right? Because there's a top and bottom. Don't we have to figure out a way of making the top number work based on these being the n values, and then what makes the bottom number work and based on these being the n values? Great. Now, I picked a nice easy one. Would you agree n on the top and n plus 2 on the bottom? If I asked you what does that converge to, would you agree it'd be 1? Be something you could do in your head. Right. How about this fella? Oh, good. It's not always my dogs that join in. Right, I need a formula that when you plug in 1, you get 1. When you plug in 2, you get 4. When you plug in 3, you get 9. And you plug in 4, you get 16. Hopefully that's obvious. What does that? When you plug in n, what do you get?
N squared.
Well done. Now, you plug in 1, you get 3. You plug in 2, you get 5. You plug in 3, you get 7. You plug in 4, you get 9. If you ignore the bottom, which is a good way to tackle these questions, do you see an arithmetic sequence?
2n plus 1.
And we have nailed it. Do you see, basically, if it's a fraction, don't you just separate the top and bottom as 2 small jobs? What makes the top number happen? What makes the bottom number happen? Then you put the pieces together, you're good. Based on this formula, will this converge? Would this sequence converge?
Yes.
Oh, a hesitant yes. L'Hopital, you get 2 over x, which becomes 2 over infinity, which is 0. So yes. And not only does it converge, this particular one converges to 0. Okay, are we comfortable about if someone gives you a sequence that you could generate its formula? There are some real interesting combinations there. And see if we can find me a little list. Check. Last chance. Is there anything in those 4 main themes from 11.1 that you'd like me to explain or to go over before I move on to 11.2? Okay, I'm good to go. So here's our hit list from 11.2. I'm going to start by talking about sigma notation. And then we're going to go right into the major question, which is for the next 2 weeks, most of what we're going to do is find out whether a series converges or not. And that's the major job. There's some other little things from time to time that you get to do, but the major job is converges or diverges. And so you are not going to just hit the button converge, and if the answer is wrong, you hit the button diverge and move on. You won't get an awful lot out of chapter 11, and you won't understand anything, and you'll probably fail the final. So let's not go there. So it does mean that you might end up spending 15 or 20 minutes in some of these later ones just to hit a button that says converges. And you've got to have the willpower to fight through that 10 or 15 minutes. Think of it as a challenge, I do. You're going to get much more benefit out of it than if you say, oh, no, I don't want to do that. I'm just going to just get this question over with. I know the temptation is there, but resist it, right? Don't go to the dark side. See, some of you do know my quotes. I've been using lots of quotes today. Okay, side issue. 42. Hitchhiker's Guide to the Universe. What's the relevance of that? What's 42?
That's the answer.
That is the answer to what?
Life, the universe, and everything.
Correct. Anybody who has not seen Hitchhiker's Guide to the Galaxy, the movie wasn't that great, so I wouldn't bother too much. But definitely go looking for the 6 BBC episodes way back in the day. Really good. Watch it. Okay. Oh, another quote. Game over, man. Game over. Which movie?
Aliens.
Which one?
Well, the second one, aliens, plural.
Yeah, OLWS. Good. Yes, the second one.
By the irreplaceable and sadly late Bill Paxton.
Yeah. Yeah, I read about that. That's sad. People shouldn't die before their time. I don't know what that means, but a lot of people seem to die before they should. He probably had a few good movies left in him. And I'm sure he's quite disappointed the fact that he's dead as well. Yeah. My dad had a great quote that he was always quoting about all sorts of situations. He would say that you should always enjoy your life because you're a long time dead. It's kind of good philosophy. I try and enjoy myself. It's probably one of the reasons why I vary all over the place. Because I just had fun there. There was no mathematical context to anything we just did, but it was fun. Okay, let's look at series now. Let's look at sigma notation. And in particular, why it's necessary in series. Well, imagine I had a guy called this fella. Now, if I wrote down some of its terms, be 1 over 1, 1/4, 1/9, 1/16 to the end of the universe. And we call that guy a sequence. There's a guy called S, which we call the series, or sometimes the series of the sequence, but normally we just say the series. And it's a single thing. And it's what you get when you add all of those guys up. And there are some series that converge to a number. Actually, I believe this one converges to pi squared over 6, but that doesn't matter. There are some that converge to a number, and then the other half diverges. Now, diverges, just like in sequences, means sometimes that it adds up to infinity. In other words, if you keep on adding terms and terms, it just gets bigger forever, right? A very simple example of that would be 1 + 2 + 3 + 4. Forever, right? Would you agree that if you did that forever, the answer would be infinitely large? And we call those ones diverges. And we don't need to say to infinity. But can you imagine a sequence that looked like this? Not very interesting, 1, but can you imagine that you were adding 1, -1, 1, -1 forever? What would happen if you continue to do that to the end of the universe, right, to infinity? Would you agree it wouldn't be homing in on one value? Wouldn't it be bouncing between 1 and 0s? And if it ended up in 1, then somehow you know that infinity is an odd number. And if it ends up in 0, somehow you've figured out that infinity is an even number. And we know infinity doesn't actually stop. So can you see that that counts as a diverge? And this fella, which is the one to do with the poor frog, remember that one? It converges. And when you converge to a number. In this case, you converge to 2. Now, this might surprise you, or maybe it won't, that when we try and find the value of a series, and that could mean it diverges to infinity or it's 2, we spend almost all of our time only proving that it converges. Most of the time, once you know that it converges, it's very, very difficult to find out what it converges to. We know that it adds up to some number, and you might think, well, surely you should be able to find it, you know, like the limit as it tends to infinity. Surely there's some algebra out there. But actually, there's not. There are many sequences in the universe that we know converge, but we do not know what they converge to. What we can tell you is to 10 decimal places what it converges to, or 1,000,000 decimal places. All you do is you go to your computer and you say, hey, could you add up a couple of billion of these terms together and tell me what the answer is? And you will get an answer to as many degrees of accuracy as you like of what it converges to. But we won't be able to tell you it's √3 over e squared, right? We won't be able to tell you that. It's exact value, which is strange, but that's what it is. Now, if you want to write down a series, you could basically write it this way. But that gets, well, it's kind of unsatisfying. You know, mathematicians are lazy and we don't like to write things like that. And secondly, don't you kind of have to know what the formula is to figure out what the next term is if you wanted to know what it was? It'd be a rather cumbersome way to do it. So we have this fella called sigma notation. And I'm going to do the n equals 1 to infinity version. In this particular question, this fella goes here. This represents the series. So if you've never seen sigma notation before, sigma means you're going to add stuff. And you're going to add stuff by using a variable called n, and you're going to plug in 1, then you're going to plug in 2, then you're going to plug in 3, 4, and 5, and each time you do it, you're going to add it to whatever was there before. So you can imagine that would be 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, to infinity. And sigma notation is the go-to technique for writing down in a very concise format what a series is. So for instance, if I write a series down and I call it n equals 1 to the infinity of that guy, for example, are you all comfortable? You know what you're being asked to add here. And if you wanted to see some values, you plug in 1 and you get a third. You plug in 2 and you get that guy. You plug in 3 and you get that sign. Why am I doing that? There's pluses, right? And forever. Exactly the same guy. The variable that I'm using here is n. The variable I'm using here is k. It's called a dummy variable. I mean, it could be any letter of the alphabet. Some textbooks like n I actually like N for a change, but some books like K. And there's a reason why K will get used by me sometimes as well. But that's quite a cool one, right? And couldn't you do, I don't know, M equals 1 to infinity, M over 2M plus 1, and it would mean the same. Are we good so far? Okay. Diverge. You gotta be one or the other. You definitely can't be both at the same time. So how do we check if a series converges or diverges? Well, let's give you an example of one. The harmonic. On Thursday, we talked about this and some of its family members, because you can put pluses and minuses as well. When you take this guy, it diverges to infinity. Why? Because I tell you it does, if you like, but it does. Now, any member of its family also diverges. Now, you might think that the individual terms go to 0, because they do. But they go to 0 so slowly that when you add them all up, the answer could be infinite. Now, that might seem like a contradiction. It's not. If you take the next 4 terms, right, a third, a quarter, a fifth, and a sixth, if you add those 4 guys together, you get a fraction that's bigger than a half. If you then take the next 8 fractions together and you add them up, you get a fraction that's bigger than a half. Then you do the next 16, then the next 32, and so on. Since it's an infinite line, can't you do that infinitely often? So what are you saying? You're saying that this is made up of 1 plus a half plus an infinite number of other halves. Would you agree that an infinite number of halves is infinitely big, and therefore it diverges? So that's a kind of pseudo proof of that. Or you will just remember that when you ever see this guy, you've got a diverger. Now, you are going to see from time to time guys that look like that. You'll also see guys that look like that. Guys that look like that. And guys that look like that. The thing that makes all of these guys belong to the same family is that they are either geometric series or they're darn close to being a geometric series. Now, the shape of them is typically, at least for these here, a number and then something to the n, something to the n minus 1, something to the n plus 1. If you see a series that's made up of a formula that contains something to the n minus 1s, as you can see in all these examples here, you're looking at a member of the big family of geometric series. So we have a test called the geometric series test. And what it says is that if you have a guy that looks like this, find the absolute value of I. the common ratio. And if this guy is technically less than 1, not equal to, but less than 1. So if I write it out in all its majesty, it's that one. Do you see that it's almost the same as the geometric sequence, but 1 is not allowed now? If the R value is in this range, the series will converge. And not only will it converge, I can also tell you what the sum of it is, what the series adds up to. And it's given by this formula, A over 1 minus R. So some questions will ask you for the sum, other questions will just say, does it converge or diverge, right? Now, once you know this piece of magic, that if R is between -1 and 1, that it will always converge, and that the sum of the series will be that. Let's go back to this fella here. Do you recognize who R is from its formula? Because it's there, you just have to know where to look. Okay, what's the R value here? In this question here.
1/2.
Agreed. What's the R value here?
2.
Got to think this one a little bit sneaky. You can do some algebra on it if it helps. I might do that to prove to you. What fraction is the R value in this third one?
3/4.
I know this one has a 2, but we can argue that the 2 is not that important in the long run, because that thing in the bottom will kill it, right? It'll be so negligible it won't matter after a while. In this last one, I can't tell you what the sum is, but I can at least tell you whether it's going to converge or not. In this question here, what fraction will R be?
3/5.
Right. Now, the fact that some of you gave me the answer is good, but the others might be saying, what the heck's he just done there? Where did these guys come from? Well, if you write down the general version of every arithmetic or geometric series in the world, that's the general formula. Do not worry about the n-1. That's just what happens. That's just the way it comes out. What's important is it the exponent, not the exponent, is it the base of the exponent, the base of the power, the R value. So R is 1/2 here. R is 2 here. What about the 4? Doesn't matter. It's not the R value. The 4 comes in later, but not right now. If you take this fella here, right, this one here, and you're not convinced about the 3/4, then couldn't I call this guy 3 times 3 to the n-1 and make this guy 4 to the n-1? Couldn't I separate out the 3 and make that 3/4 to the n-1? Do you see the 3/4 now? That could have been n plus 1, or it could have been n. The R value really is quite resilient, right? It doesn't change because of n or n plus 1, so it doesn't affect the R. It affects other things, but not the R. So that means converges, converges, oops, diverges, converges. The R value is between 1 and -1, converges. The R value 3/4, converges. The R value is 2. Well, if you're not a converge, right, you're a diverge, right? So whatever's left over is a diverge. So R is 2 is a diverge, and R is 3/5 here, right? Less than 1 considers. Now, what would some negatives look like? Well, if I stuck a negative here and maybe a negative here, it wouldn't change too much. wouldn't the R value now be negative a half, but it would still converge? And wouldn't the R value be negative 2 and it would still diverge? So the plus or minus really doesn't have any major effect on the conclusion about converging or diverging. Now, for the ones that converge, which would be 1, 2, and 3, these two are pure geometric sequences, and therefore this formula would work. This one here, you would only be asked, does it converge, and nothing else. So let's separate out two of these questions and look at what does it converge to. So one of the guys I had, at least one of its versions, was this. So that's that guy. Now we know it converges, and the R value is a half. Now A is the first term. Now if you plug 1 in here, you get 3 times a half to the 1. 3 times a half is 3 halves. Are you happy about where I got the 3 halves from? You plug in 1, and whatever comes out, that would have been your first term, right? That would be your A. Now the sum is A over 1 minus R. In this case, it's 3 halves over 1 take away a half. 3 halves over a half. Can you trust me? That's 3. So if you wanted to add up this series, it would add up to 3. Now, the second example. This one also converges. The R value we decided was 3/4, and its A value is 3 to the power of 1, which is 3, and 4 to the power of 0. Please don't tell me 4. 4 to the power of 0. So actually A ends up being just 3. So it adds up to A over 1 take away R, which is 3 over 1 take away 3/4, 3 over 1/4, and it ends up being 12. So if you wrote this fella down to eternity, it's rather surprisingly a large number. It would converge to 12. Now that's one of the very, very few series that we actually know a formula that will allow us to calculate what the converging ones add up to. You don't need to worry about diverging, because the answer is they don't add up to anything, right?